if I run this application, sort the numbers. This is JNI demo sorting arrays in C++, Kotlin plus NDK. We are using the native development kit over here. Basically, in this app, we are building a tiny Android app that calls the CPP code through JNI to sort an array, and you will see that Kotlin side also. I will explain the CPP code as well as the Kotlin code over here. So and I will document the code as well. So as you can see over here, this is the input 5391156, and it is sorted in the ascending as 125569 and descending as 695521. Okay. I'll show the project structure first. This is the Kotlin code main activity.kt. This is the CPP code sort underscore cpp.cpp, and this is my CMake list file. So Kotlin file will declare the external functions. These are the external functions: string from JNI, sort ascending, and it will take as input as array input, integer array input, right? And these functions will be implemented in the CPP. These functions are implemented in the CPP. Then we have make a CMake build to produce the shared library. This is Kotlin code. Native method is implemented in CPP, right? Maybe these functions are implemented. We will just write some information. This we create an integer array of 5291 and give an input over here. And call the native methods. So native methods, and we are passing the integer array of over here. Where is native? Yeah. Okay. So why we are using JNI? JNI will be the bridge between the Kotlin and CPP. Kotlin cannot call CPP directly, so we give the JNI bridge, which exposes the CPP function with specific name and signature, so JVM can match and call them. We have a CPP file, that is JNI side file over here. This is the top of the CPP file, and we include a header, that is jni.h, and put our functions inside this externc to prevent C++ name mangling. Compiler rewrites the function class into long unique symbol names into the compiled binary, so the linker can be overloaded and namespace functionality. Then we have JNI naming rule, that is important. Highlight the comments and names. JNI function name follow this pattern. Here is the JNI function name over here. Java underscore, then your package name where they will be used. Com underscore example sort1 CPP, where is it? Com1 sort1.cpp. Underscore class main activity, this is the class and this is the class method. Okay, तो वो कहाँ पे यूज़ कर रहे हैं उसका नाम भी it should be proper. It should be known. Then we have native methods over here. 3 native methods. Native string from JNI, sort ESC and sort decrement that we have defined over here. ठीक है. This is the name of the function. ये fix होना चाहिए. This one returns what? This one returns a J string. Active function sort. This will sort in ascending whatever it will do, so it will sort in ascending order. It is getting input. To delete the original array, we will pass the new array from here. Okay. As you want decrementing also. If you delete the original array, then decrementing can happen, but it will not be proper. It will be not for the input, it will be for my this mutilated array. Okay, so this is the name that will set the name of my project. Okay. इधर ही तो हमने नाम लोन आती रही ठीक है. If you want to see that so library, it will be somewhere here. Here's my project. JNS sort. This is the so library over here. No, I forgot to share it. This is the so library. If you go to this path, you will find the LibreSo library over here. Plus wire button.
In this video, we are going to talk about sort in C++ SQL. Sort is a general purpose library function for sorting any types of input. It is mainly used for sorting data stored in containers which allow random access. And example containers which allow random access are arrays, normal arrays, vectors, and DQ. These are some containers which allow random access. Random access means you can access IF items in constant time. So sort can be used to sort elements for all these containers. Here is an example of sort function. We have an array with these values 10, 20, 5, 7, and we call the sort function. The sort function in C++, it receives two addresses or two iterators. The first iterator or address is an address of the first element, right? So array name is C in C++, it gives you the address of first element. So your first address is address of 10. And the second address is the address after the last element, right? So this address is after the element 10. So if you talk about vector and DQ, it's going to be v.end. Right?
Because it gives you an iterator pointing to an element beyond the last element. So that is why for arrays, we do not pass array plus n minus 1 because that will give you address of last element. But we pass array plus n. That gives you the address of an element beyond the last element. This sort function is defined in algorithm library. We have two ways to call the sort function. One is just passing two iterators, and this way sorts your input array in increasing order by default. And there is another way where you can specify an order. So I've called two ways here sort by passing two parameters and by passing three parameters. So the third parameter specifies the order in which you want these items to be sorted. It's mainly a function. So the third parameter is mainly a comparison function that decides how elements are to be compared. Greater function in C++ is a general purpose comparison function which reverses the order. So the general order in increasing order, greater function gives you decreasing order. So we now know sorting. We know how do we call it using two ways. Let's guess the output of this program. So the first sort will change this array to 5, 7, 10, 20. Right? And then you print content of this array. So you will get output as, so output of this program is going to be 5, 7, 10, and 20. Now you call this sort again with greater function as a parameter. So what greater function will do? It will cause this sort to compare elements in such a way that greatest element comes first. So output of this part after calling this function is going to be 20, 10, 7, 5. So this part sorts your array in decreasing order, right? That's what you get here. And this is done because of the sort call. And this sort call changes your input array to increasing order. And that's why you get this output. Let us now talk about an example to sort a vector. We are given a vector and we want to sort it. So this vector initially contains 4 elements, 5, 7, 20, 10. We call the sort function. In sort function, we can call two ways. First way is passing two iterators, where the first iterator points to the first element and second iterator points to an element beyond the last element, right? So we pass v.begin and v.end here. In case of arrays, we pass the address of first element and address of an element after the last. So v dot begin and v dot end, and by default we get the elements in increasing order sorted. So this line prints the output as 5, 7, 10, 20. Here we have called the sort function again, but we have passed another parameter, third parameter, which specifies the order of sorting. And greater function is typically used to reverse the default order. Default order is increasing order, and greater is going to change it to decreasing order. So the output after the sort called is 20, 10, 7, and 5. So when you pass the greater function as an argument, it reverses the order and you get the array in decreasing order. So this for loop prints this part and this for loop prints this part as an output. We have talked about simple sorting where we were sorting in increasing order and decreasing order. Let us now talk about an example program where we want to specify our own order. I've considered a structure which represents a point in 2D space where x and y coordinate values, and I've written my own comparison function here which is used to sort these points in increasing order of their x coordinates. Right, so this is my own comparison function and this is structure. We are going to sort an array of this structure. So we create an array of the structure and now we call the sort function using same parameters, array and array plus n, address of first element, address of an element beyond the last element, and we pass our own comparison function. The third parameter. After sorting, all the elements of this array will be sorted according to increasing order of x value. So when you print the output, you are going to get the output as, so you have three values. So the first smallest x value is 28. So you will get 28. Then the second smallest value, 310. Then the last value, 54. So your points are sorted in increasing order of x values. Now say you want to modify your order and you want to sort them according to y values. What changes you will make in this program? You will simply modify your my comparison function and you will put y here. And the output is going to change. The output is going to change and this time we are going to get values in increasing order of y values, right? We are going to get 54 first, then 28, then 310. Now say we want to further change our program. We want to print all the points in decreasing order of y value. So what changes you will make? You will change your comparison function to this form. Now it will sort all your points in decreasing order of y. So what will be your new output? Your output is going to be 310, the largest y value, then the second largest y value 28, and then the third largest y value 54. This is output of this modified program. Let us now talk about time complexities and internal working of sort function. Sort function internally uses quick sort. And if you talk about more details, it is a hybrid of quick sort, heap sort, and insertion sort. By default, it uses quick sort. And if quick sort is doing unfair partitioning and going to take more than n log n time, it switches to heap sort. And when your array size becomes really, really small, it switches to insertion sort. So worst case performance and average case performance of sort function is n log n. Also the number of comparisons it does, it's n log n. So it's an n log n algorithm, which is an optimal time for any general purpose sorting function, and it internally uses intro sort. Let us talk about this problem. We are given an array of items where every element of this array represents value of that item. And consider a thief which sees all these items with different values, and this thief can pick only k items, right? He's not allowed to pick more than k items. So the thief is allowed to pick k items and he wants to collect maximum value. So let's understand the problem with this example. Here is an array of items, k is 3, so thief can pick only 3 items. So thief has many options. He can pick these 3. For example, he can pick 3, 2, 5. What value he will collect? He will collect 3 plus 2 plus 5, 10. And if he picks these 3, say 7, 5, 12, what value will he collect? 24, 7 plus 5 plus 12. So how will the thief pick maximum value? Thief has to pick 30, 12, and 7. That's how the thief is going to pick 49. Let's now see this example. In this example, the thief can pick 4 items. So what items thief is going to pick? Thief is going to pick 80, 50, 20, and 10. That's how the thief will get the value as 116. Let's now talk about solution of this problem. How will you solve this problem? You need to write a function that will take an array as an argument. This value k is an argument, and a function should return the maximum value thief can collect. Please pause this video now and think of a solution that solves this problem. I think you must have guessed the solution. The solution is to find k largest items and return their sum, right? And there is a super naive way of doing it. Super naive way is to find the first largest item, right? And then find the second largest item, then find the third largest item. For example, here we need to find only 3 largest items and return their sum. This super naive solution has big O of n squared, n into k time complexity, right? You need to find largest items k times. So upper bounded by big O of n into k. Now please pause this video and think of a better solution to solve the problem. Here is a better solution to solve the problem. The idea is to sort the array in decreasing order. So we have this array, we sort it in decreasing order. So 30 comes first, then 12, then 7. After we sorted the array in decreasing order, we simply need to print the sum of first k elements. Those are the largest k items. So after sorting, we initialize the result as 0, then we run a loop and do a sum of first k elements and then return the result. Please note that to sort the array in decreasing order, we need to pass this greater function. And also one more thing, we could solve this problem by sorting the array in increasing order also. We can sort the array in increasing order and then run a loop so that we get the sum of last k items. That's another way of implementing it. Now let's talk about the time complexity of the solution. This solution requires n log n time to sort the array and then big O of k time to do sum of k largest elements. So the overall time complexity is n log n because k is definitely smaller than n. Now the question arises, can we do better? We have talked about a better solution to solve this problem in priority queue track. We have talked about a problem there, find k largest elements, which is same as this. So using priority queue, we can do it in better than n log n time. Hi, in this video, we are going to talk about fractional knapsack problem. We are given a set of items, I1, I2, I3 in this case. We are given their weights. Weights are 50, 20 and 30 respectively. I1 has 50, I2 has 20 and I3 has 30. And their values. I1 has value 600, I2 has value 500 and I3 has value 400. We are also given a knapsack of given capacity. We have a knapsack, or in simple words, we have a bag of capacity 70 and our target is to collect maximum value in the knapsack. And the advantage that we have in this problem is we can collect some items partially. We consider items in sort of powder form where you can weight some part of this item and pick some part of this item, fraction of this item. That's why we call it fractional knapsack problem. Let's see this example. We have capacity 70. We have these weights. So how much you can collect maximum? We are getting the output 1140 because we can get 1140, which is the maximum possible value, by picking this item completely, I2 completely, I3 completely. So with I2 and I3 we get 900 and we have collected 50 kg so far. 20 kg is still left in knapsack. So we pick 20 kg of this 50 kg item, right? So this much we pick of I1, 20 divided by 50. And if you do some of these values, you get the value here as 500. Here you get the value as 400. And here you get the value as 600 multiplied by 20 divided by 50. So this value turns out to be 900 plus 240, which is 1140. That's the total value we are getting here with this configuration, right? You can try other possibilities, like if you take this item completely and this item completely, you get 1100, right? But 1140 is more. For example, if you take this item completely and take this item partially, you will not get more than 1140. Let's take this example. So if I take 600 of this and if I take 20 of this, how much I'll get? I'll get 600 plus 400 multiplied by 20 divided by 30. This much I'll get, right? So this is definitely less than 1140 because, we are taking partially 400. Together 400 itself makes 1000, right? So we are not going to get more than 1140. So that's the optimal result. And you need to think of an approach to get this optimal result. Let's see another example. In this example, we have three items, I1, I2, I3, and their weights are 10, 5, 20. And values are 200, 50 and 100. Knapsack capacity is 15 kg. So how do we get maximum value in this knapsack of 15 kg? What we do is we pick this item completely of 10 kg and we pick this item completely of 50 kg. So we get the value 250 with I1 plus I2. This is our configuration which is giving us maximum value. You can try other combinations. You will not get value more than 250. 250 is the optimal answer for this. Now please pause this video and try to write down a program that takes an array of items where every item is represented by a pair. A pair has weight and value. You need to return the maximum value that you can collect. As an input, you are also given knapsack capacity together with this array of items. Let us now see implementation of the fractional knapsack problem. Let's understand the solution and implementation with this example. Let's say we have an array of pairs where the first item of this pair represents value of the item. The second entry of this pair represents weight of the item. So we have three items to be picked. First item has value 120, weight 30. Second item has value 100, weight 20, value 60, weight 10. And we have a knapsack with capacity 50. So the first thing we do is we try to find out items which have maximum value per unit weight. Because it's a fractional knapsack problem, you can consider the items in the powder form. So if there is an item whose value per kg is 100 and there is another item whose value per kg weight is 10, you will obviously try to fill your knapsack maximum with the value per weight 100 kg item, right? So that's what we are doing here. So value per weight for this item is 4. For this item it's 5. 120 divided by 3 is 4. 100 divided by 20 is 5. 60 divided by 10 is 6. So we sort these items in decreasing order of value per weight, so that we can pick the maximum value per weight item first, then the second maximum value per weight item. After sorting, we get 60, 10. This is the maximum value per weight, 6. Then we get 120, then we get 120, 30. After sorting these items in decreasing order of value per weight, we start filling our knapsack by traversing the sorted array. So our knapsack is capacity 50 and the first item has value 60 and weight 10. And when you are at the current item, you try to fill the knapsack maximum possible with this item. Basically, you take the full current item if you can take the full. And if your knapsack does not have enough capacity, then you take it partially and fill your knapsack, right? So we start from here and we have this item with 10 kg and we have knapsack 50 kg. So we take the whole 10 kg and fill it in our knapsack. So we collect the value 60, but our knapsack now has capacity 50 minus 10, which is 40. Now we go to the next item, and this is 20 kg, knapsack is 40 kg, so we take the whole 20 kg, and we get the remaining capacity as 20 kg, and the value that we collect is 100. So total value that we have collected so far is 60 plus 100, 160. Now we go to the next item. Next item is 120 value, 30 weight. Now our knapsack has 20 weight. So we can't take this item completely, we take the fraction of this item. So if you take 20 kg of this item, how much value you will collect? So value for 30 kg is 120. What will be the value of 20 kg? It will be 120 multiplied by 20 divided by 30. So that's the value we are going to collect by the last item. 20 divided by 30 multiplied by 120. This is going to give us 80, and 80 plus 60 is 240. So the answer for this input is 240. And how are we getting this answer? We are first sorting all the items according to value per weight, and then we are traversing the items and we are picking items one by one. And you can notice one thing. If you see an item which cannot be completely filled in the knapsack, then you partially fill it, and that's your ending point. After that, you don't need to pick any more items because the knapsack must have been filled. If there was capacity left in the knapsack, you would have taken more of this item only. So that's the idea for implementation, and here is C++ STL implementation of this idea. We are first sorting the array according to their value divided by weight ratio. So we have ARR, first iterator, last iterator, end iterator, and then we have my comparison function. What my comparison function is doing, it's taking the value divided by weight for the first item, value divided by weight for the second item, and it's putting the higher value divided by weight at the first position at the beginning when it compares two items. So this is how these items are sorted. Then we initialize the result as 0. Then we traverse through all the items one by one, right? Capital W is the capacity of knapsack, current capacity of the knapsack. We compare the weight of current item. If it is smaller than or equal to the knapsack capacity, we take this item completely, add its value to the result, and subtract its weight from the current capacity of the knapsack. That's how we update the capacity. Now, if this item cannot be taken completely, then we take it partially, compute its partial value by taking the value of this item, multiplying it by the current capacity of the knapsack, and dividing it by the total weight of this item. That's what we did here. And we update the result, and this must be the last item because we could not take it completely. So we break out of the loop, and at the end we return the result. So this is the implementation of this fractional knapsack problem. Let's now talk about the time complexity of the solution. We are sorting the array, so it's going to take big O of n log n time, right? And after sorting the array, we are simply traversing the array. So it's going to take big O of n time. So overall time complexity of the solution is big O of n log n. Hi, in this video we are going to talk about chocolate distribution problem. We are given packets of different sizes where first packet contains 7 chocolates, second packet contains 3 chocolates, third packet contains 2 chocolates, last packet contains 56 chocolates. So these are number of chocolates in individual packets, and we have an array of packets. And there are m children. So in this example, we have 3 children. Now we want to distribute these packets to these m children with these rules. The first rule is every child should get exactly 1 packet, not more, not less. The second rule is we want to minimize the difference between minimum chocolates that a child gets and the maximum chocolates that another child gets. So we want to distribute 3 packets to these 3 children because every child should get only 1 packet, right? So we need to pick 3 packets from this array such that difference between minimum and maximum of these 3 picked elements is minimum. Say you pick these 3 elements. What is the difference between minimum and maximum? 5, right? Say you pick these 3 elements, 7, 3 and 4. What is the difference between minimum and maximum? 7 and 3, 4. Say you pick these 3 as elements. What is the difference between minimum and maximum? 2. Say you pick these 3. What is the difference? 7. Say you pick these 3, 9, 12 and 5. 9, 12 and 56. What is the difference between minimum and maximum? 56 minus 9, 47. Out of all these differences, 3 to 4, these 3 elements, these 3 values form the minimum difference. And the difference between minimum and maximum for these 3 is 2. That is why output is 2. So we need to produce the minimum difference in a set of m elements. So we need to pick m packets such that the difference between minimum and maximum is minimum. Let's see this example. In this example, if you pick 3, 4, 7, 9, 9, then you get the minimum difference. 3, 4, 7, 9, 9. The difference that you get is 9 minus 3, 6. If you pick any other combination, you will not get difference less than 6. For example, if you pick 1, 3, 4, 7, 9, what will you get? You will get 9 minus 1, 8, which is more than 6. So that is why the output for this example is 6. Please pause this video and try to think of a solution for this problem. The expected time complexity for the solution is big O of n log n. To find the result, we need to pick m elements, right? Such m elements which have the minimum difference between minimum and maximum. What if I do this? I consider every element as minimum of these m elements, right? And then I find remaining m minus 1 element for this element, and then I say what will be the set when this element is minimum? What is the minimum possible difference I can get with this being minimum, right? So if I consider 7, I can get 3 elements as 7, 9, 12, and I can get the minimum difference as 5. If I consider 3, I can get the minimum difference as 3, 7, 9, and I can get the difference as 6. If I consider 2, I can consider 2, 3, 4, and I get the minimum difference as 2. So this is where I get the result. So if you look at this pattern, what are we doing? For every element, we need m minus 1 greater elements than this. We mainly need the element which is just m minus 1th greater element than this. If I find the difference between that element and this element, I can find the difference for this element being the minimum of the result. So the idea is this: you sort the array. You traverse the array from left to right. Let's take this array and let's see what do we get after sorting. We get 2, 3, 4, 7, 9, 12, 56. Now if I want to find the set with 2 being the minimum element, I can find by subtracting 2 from this, right, which is array of 2 minus array of 0. If I want to find the set of m elements where this element is minimum, I can find it. The difference between for this set is array 3 minus array 1. For this set, the set where your 4 is the minimum element, what is the minimum possible difference? 9 minus 4, 5. So for every element, you just need to go to array I plus m minus 1, right? For array I, you need to find the difference between array I plus m minus 1 minus array I after sorting. That's all you need to do is. Now, after you sort the array, you initialize the result as the first minimum element, right? This 3 after sorting. This is your initial result value. Then you traverse for all the remaining elements starting from the second element. So you start from here, right? And what do? For this element, you find this difference, array 3 minus 1 here. And you compare it with the current result. If this difference is smaller than current result, you update the current result. Then you go to this element. And what do? You find out array 4 minus array 2. So in general, if I want to write this expression, this is what this expression is. I plus m minus 1 minus array I. If I go to array 3, I need to do array 5 minus array 3, right? So that's how I'll continue while I plus m minus 1 is smaller than n, right? So I'll consider every element as starting element of the set and will find the minimum difference with this being the starting element, and then find the overall minimum difference by comparing the current minimum difference with current result, right? So let's do a dry run for this array. After sorting, we'll do array m minus 1, array 0 as result. So our result is going to be array 3 minus 1 minus array 0, which is going to be array 2 minus 0. So result is going to be 2. So this is our initial result. Now we run a loop for I equal to 1 and I plus m minus 1 smaller than. So what happens when I becomes 1? You will see the current result and I plus m minus 1 minus array I. So I plus m minus 1 is this, 7 minus 3, 4. You will compare 2 with 4. So 2 is anyway smaller, your result remains 2. Now you will come to this element and you will compare 9 minus 4, 5 with result 2. So your result will remain 2, right? Next time what you will compare? 2 and 9 minus 4, right? So then you will come to this element. You will compare 12 minus 7 with 2. 12 minus 7 with 2. So your result remains 2 because this is greater. You want the minimum difference. Next time when you come here, you will compare 56 minus 9 with 2. So next time you will have 56 minus 9. Right, you will have 47 here. So your result remains 2. And at this point you will stop because your I plus m minus 1 will become n next time, right? When you come here, I plus m minus 1 will become n. So you stop and your result remains 2, you return the result. So what is the time complexity of this? This is a big O of n log n solution. We first need to sort the array. Let us talk about this problem. We are given an array where elements might appear multiple times. Our task is to sort this array according to frequency. What it means is the highest frequency item should appear first. All occurrences of this highest frequency item should appear first, then the next frequency, then the next frequency item. And if there are two items which have same frequency, then we need to put the smaller value first, like the normal sorting order. Let's understand the problem with these examples. So in this example, we have an array which has these elements 10, 5, 20, 10, 10, 5, 20. We wish to sort it in decreasing order of frequencies. So 10 is the most frequent item, appears 3 times. So we have all occurrences of 10 first. Then 5 and 20 have same frequencies. So to pick one of these two, we compare them, and 5 is smaller. So we put the smaller item. So we have 2 occurrences of 5 and then 2 occurrences of 20. Let's see this example. Here we have 2 items and both have the same frequencies. 1 is frequency 2 and 2 is frequency also 2. So we need to put the smaller value first. So we put 2 occurrences of 1 and then 2 occurrences of 2. So we need to sort this array according to frequencies. All occurrences of the largest frequency item first, then next, and if 2 frequencies are same, then put the smaller value item occurrences. Now please pause this video and try to write down a solution that takes an array as an argument and sorts the array according to frequencies. Let us now see the implementation details of the sorting approach. What we do is we use an unordered map and we store array elements as keys and their frequencies as values. So whenever we wish to find frequencies of items, unordered map is the data structure which is always used because it finds the frequencies very efficiently. So we build an unordered map where we have array elements as keys and their frequencies as values. And the order in which these pairs are stored in this unordered map is not known. It's implementation dependent on the how hashing is implemented internally. So just put one order and your implementation might be storing them in any other order. Now once we have built an unordered map, how do we sort these items according to the second value of the pairs? So what we do is we put these items into a vector because vector is a random access container and we can sort the vector using sort function. So we traverse through this unordered map and we put these pairs in a vector. So we make a vector of pairs. After we have made a vector of pairs, we sort this vector of pairs such that the sorting function follows the criteria according to the given question, that the most frequent item should come first, and if the frequencies are same, then smaller value should come first. So we need to write our own comparison function to achieve this. Now you have enough idea which containers to use, how to apply the sorting. Please pause this video and try to write down the complete code. Let us now talk about implementation of the approach. So we have a function sort by frequency that takes an array and size of the arrays and arguments. For example, if this is your array, it modifies the array and changes the array to this. How does this work? It first uses unordered map to store the frequencies of items. Once it has created an unordered map like this, frequency item is frequency, item is frequency. Please note that we call it unordered, so order is not defined. So these items can be in any order, these pairs can be in any order. I've just written one of the possible orders. Now we create an unordered map. Once we have created a map, we need to sort these items according to frequencies. And if the frequencies are same, then we need to sort by values. For that purpose, we copy the contents of this unordered map to a vector. So we have created a vector of pairs, right? And we have used this constructor that we typically have in C++ containers, where we can pass begin and end iterators of other containers. So what this constructor does, it takes the elements of the other container from begin to end and takes those items and builds the new container. So we have created a vector container using the map container items. So it creates a item, its frequency. Please note that we call it unordered, so order is not defined. So these items can be in any order, these pairs can be in any order. I've just written one of the possible orders. Now we create an unordered map. Once we have created a map, we need to sort these items according to frequencies. And if the frequencies are same, then we need to sort by values. For that purpose, we copy the contents of this unordered map to a vector. So we have created a vector of pairs, right? And we have used this constructor that we typically have in C++ containers, where we can pass begin and end iterators of other containers. So what this constructor does, it takes the elements of the other container from begin to end and takes those items and builds the new container. So we have created a vector container using the map container items. So it creates a vector of pairs. So whatever was there in the map is copied to the vector. And once we build the vector, we simply sort the vector because now we have a random access container. We can sort it. Now to sort the vector according to the criteria that we have written our comparison function. And we pass this comparison function as an argument to the sort function. And how does this comparison function works? It takes two pairs, and to decide which pair to go first, it compares their second values first, which are frequencies, and if frequency is the same, then it puts the smaller value item first, which has the first. So these are actually pairs. You can access the frequency or second item using second, and you can access the first item using first. So if the first item is smaller, then you put the first item first. And if the frequencies are different, then higher frequency item goes first, right? So that's the rule we follow for sorting. And once you follow this rule and you sort this vector, you get this. Top frequent item comes first, right? It has the higher frequency than anything else. Then the second top, and we have two items at second top, but we put the smaller value by this rule, right? So 22 comes next, and then 32 comes. After we have built this vector, we need to modify our original array. For that purpose, we have this copying step where we use I as an index in the original array. We use this for each loop to traverse through every pair in the vector, right? And for every pair, we find its second value, how many times this pair appears. For example, this is our x. So x dot first is 10 and x dot second is 3. So we run a loop x dot second times, 3 times for this example, and copy this 10 3 times in our original array. So 10 comes 3 times in the original array. We simply overwrite the content of the original array. Then we come to this item and copy 22 times in the original array. Then we come to this item and copy 32 times in our original array. So after copying, our vector modifies to this, and this is what we wanted. So we have sorted a vector according to frequencies. Let us now talk about time complexity of the solution. So this is big O of n step. We are building an unordered map, and then we use a vector. So construction of vector is again big O of n from an unordered map. Now we sort the vector. This is big O of n log n step. And then we are copying the items from vector to array. So we have total n items in the array. So we are going to take big O of n time. Please note that this big O of n log n is an upper bound. Say if there are only 5 distinct items in an array of 1000, then it's going to take 5 log 5 time, right? Not 1000 log 1000. So it's actually d log d, where d is the number of distinct items in the array. So that's the overall time complexity. We can say it's big O of n plus d log d, where d is the total number of distinct items in the array. Let us talk about this problem. We are given an array of items. We need to sort these items according to their frequencies. The top frequent item should appear first, then the next most frequent, then the next most frequent, and the last item should be the least frequent. If there is a tie, then we need to break the tie by picking the element which has leftmost first appearance. Let's understand the problem with these examples. Let's say we have this array. So which element is the most frequent here? 10. 10 appears 3 times. So our first element is 10. Then next we have 2 elements with the same frequency, 5 and 20. 5 has frequency 2 and 20 has frequency 2. Now which one should we put first? We break the tie by picking the element whose leftmost appearance is first. Right? 20's leftmost appearance is this and 5's leftmost appearance is this. So we pick the element 5 and we put both occurrences of 5, then both occurrences of 20. Let's now see this example. Here we have 2 items and both of them have the same frequency. So we again break the tie by picking the element whose leftmost appearance is first. So this is leftmost appearance of 2 and this is leftmost appearance of 1. So 2 should come first. We put both occurrences of 2 and then both occurrences of 1. Let's see this example. Here every element has frequency 1. So we are going to put all these elements in the same order as they appear in our input array. Now please pause this video and try to write down a linear time function to sort the items according to their frequencies. We are first going to talk about a solution that does not care about the order in case of a tie. And then we are going to extend this solution, which is going to print the element with the leftmost appearance first in case of a tie. You may pause this video now and first try a solution that does not worry about the order of elements, works in linear time, and sorts the elements by frequency. Please note that we have already discussed an n log n solution for a similar problem. The problem that we discussed earlier was slightly different. The task there was to break the tie by comparing the elements. Here we are supposed to break the tie by looking at the position of first appearance. This problem can be solved in linear time. The first solution that we are going to discuss, we are not going to consider the order in case of a tie. We are going to print the items in any order in case of a tie. Then we are going to extend the solution later to break the tie according to the required rules. Let us now take a look at the implementation of this linear time solution. In this solution, we are not going to maintain any order. We are simply going to print items according to their frequencies, and if there is a tie, then we can print anything. So the first thing that we do in this solution is we store items and their frequencies in an unordered map. It's a standard technique. Whenever you want to find frequencies of items, you use items as keys and you use frequencies as their values, and you build an unordered map. So after this step, you get this map. And after we have built the map, we have an interesting trick in this solution. The trick is to use frequencies as indexes in an array. And how does this trick work here in linear time? The reason is, since you have n items in this array, the maximum frequency that you can have is n. And maximum frequency you will get when everything is same. If all items are same, then this particular value has n frequency, right? So after we build the map, we create a vector, an array of vectors, right? And this array has size n plus 1. Why n plus 1? Because maximum frequency is n. Please note that we could create an array of size n as well. Here I have created an array of size n plus 1 for ease of implementation. We are not going to have any entry at index 0 because there would not be any item with 0 frequency, right? It doesn't appear at all. So after building the map, we traverse through this map and we build this array of vectors. And what are the contents of this array of vectors? We have these things as indexes in this array. So this 10 goes to index 3. This 5 goes to index 2. This 2 is used as an index. The 5 goes to index 2. This is index 0. This is index 1. This is index 2. This is index 3. And these are vectors. This is an empty vector. This is a vector of size 2, vector of size 1, vector of size 1. Then 20 and 30 are two items for index 1. So they both go in a vector at index 1. And we do not have any item with frequency 4, 5, 6, 7. So this is our frequency array after we have processed the map. We traverse through the map. We use values as indexes or frequencies as indexes in this array, and we go to that particular vector and we push the key to that vector, first of this pair in a vector. And once we have built this frequency array, I think you can guess the solution. The solution is really simple. You need to traverse through this frequency array from the end, because the last item will have the maximum frequency. And here the last item is empty, so we don't put anything into our original array. These 4 items are empty because there are no items with frequency 7, 6, 5, 4. When we come here, we see an item at index 3. It means this item appears 3 times. So we copy this item 3 times in our original array. Right? This is what we are doing here. We are traversing through this frequency array from the last index here, from index n. And for every index, we are traversing through all the items at this index. So this loop does not run for these 4 items because these 4 are empty. And this loop runs for this item 10 because you have an item 1 here. This loop runs once for this item. And what it does, it copies this item 3 times in our original array. And how do we get that we need to copy 3 times? Using the index of this item. This item is at index 3, should be copied at 3 times because its frequency is 3. So we copy 3 times in our original array, then we come here. We are moving from last to first. So we come here 5, it appears 2 times. So we copy it 2 times in our original array. Then we come here and these 2 elements appear once. So we copy these elements 1 times in our original array and we get the required array. So after this step, we got this map. After this step, we got this frequency array, and after this step, we got our original array modified according to the required order. Let's now take a look at the time complexity of the solution. This part is clearly big O of n, or we can say theta n, right? Because we are anyways traversing through every element, so theta n is a better term. And this part is also theta n, because there would be total n elements in your unordered map and you are pushing every item to a vector, and pushing an item to a vector at the end is big O of 1 operation. This operation is also theta n, because if you take a closer look at this operation, what are you doing? You are ultimately going to run this innermost expression at most n times, because you will have n items to be copied to the original array. Since this operation happens n times, you are not going to take more than n time by running these 3 nested loops. So overall time complexity of this implementation is big O of n. Now the question arises, how do we extend this solution? How do we modify this solution so that we get the items in the required order in case of a tie? Now please pause this video and try to modify the solution so that you handle ties really well. Please note that this solution does not handle tie because unordered map items can be in any order. There is no order guarantee. This 20 can appear later as well. So there is no guarantee of order in the solution. How do we ensure the order? Let us now see the extended solution. Here we ensure ordering in case of a tie. And which order we maintain? The element whose first appearance is leftmost is preferred. So let's say we have this array and we built this map. This part is same. The only change that we make is we replace these 2 lines with these lines to ensure the order. And the change here is, instead of traversing through the map to build the frequency array, we traverse through the original array so that we get the items in the same order. Now the problem is, if you're simply traversing through the original array, then you would end up adding same item multiple times if this item appears more than once. To handle this, what we do here is we get an item from the map, and once we get an item, we set its frequency as -1 so that this item is not picked again. And before picking an item or getting an item, we check if the frequency is -1. If frequency is -1, we don't pick it. So let's say we have built this map. Now we traverse through this array 10 and we do a lookup for this 10 in our map. We get the value 3. We go to the index 3. We add the value 10 and we change this value in map from 3 to -1. Now we come to 5. We go to this index 2 and we add 5 to this index 2 and we change it to -1. Now we come to 20. 20 we add it to the index 1 because the value here is 1. We do a lookup for this in the map. We get the value 1. So we do go to this index 1, right? And we add it there because it's not -1. And after doing it, we set it to -1. We come to 5 and 5's value is -1 in map. So we don't pick it again. We come to 10 and 10. These two 10 are also not picked again because their values in the map are -1. Then we come to 30. It's not -1. So we put it into the frequency array and we change it to -1. This way, we ensure that in case of a tie, we get the elements in the order as they appear in the original array, as their first appearance in the original array. Now, is there any change in the time complexity? Earlier, we were traversing through a map. So this was upper bounded by n because you will have at most n items if everything is different. And this is exactly theta n. That's the only difference. But our time complexity remains linear. Why is it theta n? Because we are traversing through every item of the array. We are doing a lookup into the map, which is considered as a constant operation. We are adding an item at the end of a particular vector, which we were doing something here as well. So this is also constant operation. So this is overall theta n operation. One more thing we are doing is we are setting a value in the map, which is also a constant operation. So all these operations are considered constant. That's why we have theta n operation here. So overall time complexity is still theta n, and now we have items according to their first appearance order. Let us talk about this problem. Consider a situation where you have a full day party. Party starts at 00 and goes till 23:59. You are also invited in the party and there are many other guests invited. You have list of all guests and you also know when are they going to come to the party and when are they going to leave from the party. For example, here there are two guests apart from you. The first guest is going to come at 9 o'clock and leave at 10 o'clock. The second guest is going to come at 9:40 and leave at 10:30. Please note that I have not used colon in the time to keep the question implementation simple so that we can use integers. Ideally it should have been 10 colon 30, right? 10 colon 30, but I have written only integer values. So 1030 means 1030 means 1030 time. So you have list of guests apart from you who are going to come to the party, and their arrival and departure times are going to be from 0 to 23:59, right? Because party goes from morning 00 to night 23:59. Your target is to meet the maximum guests. You want to go to the party so that you can meet the maximum guests, and your target is to find out how many maximum guests you can meet. Let's understand with this example. Here we have two guests apart from you coming. One guest comes at 9 o'clock and leaves at 10 o'clock. The other guest comes at 9:40 and leaves at 10:30. So if you go at the time from 9:40 to 10 o'clock, you will be able to meet both of them, right? From 9:40 to 10 o'clock. Let's now see this question, this example. Here you have four guests coming from you, coming in the party. And these are their arrival and departure time. Guest 1 comes at 8 o'clock, leaves at 8:40, 7 o'clock, leaves at 8:20, comes 6 o'clock, leaves at 8:30, comes at 5 o'clock and leaves at 5:30. In this party, you can meet maximum 3 people. And what time you will go to the party so that you can meet 3 people? You will be going from 8 to 8:20, right? If you go from 8 to 8:20, the first 3 people will be there. This guy is there from 8 to 8:40, he is there from 7 to 8:20, and he is there from 6 to 8:30. So if you go from 8 to 8:20, you will be able to meet 3 people. And in this question, if you go from 9:40 to 10 o'clock, you will be able to meet both the people. In this question, you get the answer 3. Can you guess the time frame around which you should go to the party? You should go to the party from 11 to 11:20. If you go from 11 to 11:20, you will be able to meet this guy. He's there from 11 to 11:30. You will be able to meet this guy and you will be able to meet this guy. You will be able to meet 3 people if you go from 11 to 11:20. So you have 2 integer arrays given to you and you need to write a function that returns an integer value. And this integer value tells you how many guests you can meet at most. Now please pause this video and try to write down a function that takes 2 integer arrays and returns an integer value. Let us now talk about an efficient solution. We are going to use sorting here. Let's see how sorting can be useful to solve this problem in big O of n log n time. The basic idea behind the solution is we consider all the timelines starting from the first arrival to last departure, and at every time we see how many guests are there, right? And whatever is the maximum is our result, right? We'll go at that time and meet the maximum guests. Now if you see this example, there are 3 guests. One arrives at 6 o'clock, leaves at 8 o'clock. The second guest arrives 7 o'clock, leaves at 7:30, and the third guest arrives at 9 o'clock and leaves at 10 o'clock. So if I draw a timeline of all these guests, I'll get this timeline. At 6 o'clock, first guest arrives. We have count of guests as 1. 7 o'clock, second guest arrives. We have count of guests as 2. At 7:30, one guest leaves. So we have count of guests as 1. At 8 o'clock, one more guest leaves. So we have count of guests as 0. So A means arrival, D means departure here. 9 o'clock, one more guest arrives. So we have count of guests as 1. So between 8 and 9, there was no guest. At 10 o'clock, one guest leaves. So we have count as 0. Now if I go through all this timeline, I can notice that I have maximum guests here, right? So this is my maximum. So this is the basic idea to solve the problem, and we are going to use sorting to implement this idea. You would love to pause this video now and implement this idea yourself. Let us now take a look at the implementation of the approach. So we have a function max guest count that takes arrival, departure and size of the arrays as arguments. What this function does, it first sorts both arrival and departure arrays. So we first sort both the arrays in increasing order. See, the point is we want all these events according to the timeline. Now we have two different events in two separate arrays. So we first sort both the arrays individually. So we get all the arrival events according to the timeline. We have all the arrival events and all the departure events according to the timeline. Now our task is to merge both the events and then keep on counting the guests at the current moment. Now this problem becomes very similar to the merge function of the merge sort. And if you take a look at this code, this is close to the merge function of the merge sort. This is what we do in the merge function. We compare array I with array 1i with the array 2j, and we do I++, otherwise we do j++. Something similar we are doing here. So what are we doing here? We have considered the first arrival here. We know that array 0 is ARR 0 is going to be smaller than departure 0 for sure, right? So we have considered beginning I from 1. We are going to begin from the second arrival. We have initialized j as 0, first departure. And since we have already gone to this event, right, we have already considered one arrival and our count of guests is 1. Our current guest is 1. Our result is also initialized as 1. It's going to be at least 1. So we have already considered the timeline when one guest has arrived. Now we are going to consider all the remaining events by merging both the arrays. So what we do, we say if current arrival is smaller than current departure, then this arrival event, the current arrival event is first. So take this event, increment the count of current guests because arrival has come before next departure, and do I++, go to the next arrival in the arrival array. And if current departure is smaller than current arrival, if the next event is a departure, then decrement the current count, and go to the next event in the departure. And whatever you do out of these two, you compare the current with the result. If result is less than the current, then you update the result. You basically are checking when you get the maximum result. So at this moment, you will have the maximum result as 2, right? And result will be updated here. It won't be updated after this. Let's now do a run of this code with this example. We have 3, 900, 600, 700, 1000, 800, and 730. We sort both the arrays, 6 o'clock, 7 o'clock, 9 o'clock, 7:30, 8, and 10. After sorting, we will initialize these values, and now we'll run this loop. Now we'll compare, our I is currently here, right? And j is here. We have initialized I as 1 and j is 0. Now I'll compare these two. 7 is smaller, so array I is smaller. We have now 2 guests. At this point, we have 2 guests. And we update the result also as 2. And we increment the I because array I is smaller than departure j, so our I must have been incremented. So I becomes 2 now. Now we do the next iteration of the loop and we compare array I with array I, which is 2 now, with departure j, which is this now. So this time our array I is greater, right? So we fall into this if condition. So we do not change I, we change j. J moves to this point, right? J comes here. And we decrement the current count and we do not update the result because current is less than result. So our j has come to 1 and our I is here. Now we are going to compare these two, right? 800 and 900. 800 is again smaller. So we are going to make the count of guests as 0 and result is going to same as 2, right? We have current as 0, right? Less than result. Now we are going to go to the next iteration. In the next iteration, our array I is smaller than departure j. So we are going to increment the current, but current is not more than result, so we are not going to update the result. So you can notice that we have actually considered all the events in sorted order because we are doing something like merge of merge sort, and at every moment we have just counted the current guess and we have compared it with the maximum guess so far, and we have updated the maximum. Let us now talk about time complexity of the solution. Time complexity of the solution is clearly n log n because we have two arrays of of sizes n, and what we are going to do, we are going to sort the first array which takes n log n time, then we are going to sort the second array which also takes n log n time. And this loop is clearly big O of n plus n, right? That's similar to merge function, and merge function takes m plus n time if you merge two arrays of size m and n. So it's big O of n plus n, which is big O of n. So overall time complexity is big O of n log n plus big O of n log n plus big O of n, which is big O of n log n. Hi, in this video we are going to talk about sort in C++ STL. Sort is a general purpose library